ago in Scotland. I was very young at the time. I didn't get older till much later. Let's go back a little bit. So I went to university in the University of Glasgow in Scotland. I studied chemistry and physics with a minor in mathematics. And then I went on and did a PhD. I stayed at the university to do a PhD, firing exotic particles into, or making exotic molecules by firing muon particles, which are particles that are made in cosmic rays, but you can also make in beam experiments, not unlike the beam experiments that Ian Anderson was talking about last week. And I would make these positive muons which behave like very light protons, and I would fire them into samples, and I'd make these exotic molecules, and I would study some of the properties of that. That was a lot of fun. I did all those experiments out in Switzerland. Came back from that and decided I wanted to change direction a little bit, and so I joined the British Weather Service, what's called the Meteorological Office, and they gave me a training in atmospheric science in addition to the physics and chemistry that I had. And then some pretty important things were happening at the time. Suddenly, just after I joined the Met Office, it wasn't my fault, but the ozone hole was discovered. Do people know what the ozone hole is? Have they heard of the ozone hole? So that's where all the ozone over Antarctica and over the Arctic during the winter months, it thins out, and the amount of UV rays can come down to the Earth becomes bigger. And so I was kind of lucky to be joining the Met Office just about the time when this story was starting to break. And we were also doing some pretty novel scientific research on that, in terms of trying to trace how air parcels would move about in the atmosphere, and how, say, chemistry and chemical evolution would happen. And because of that, we were pretty unique. And so we were invited, although we were sitting over in Britain, NASA was mounting major experiments to go down and understand what was happening, because we knew that the ozone was disappearing, but at that time we had no idea why ozone was disappearing. And so I got to be part of a large team who went down and tried to understand and simulate these things. And we got involved with these really fancy research aircraft. That's an ER-2. It's a kind of civilian version of the U-2, which is the spy plane that they used to fly over Russia. But this one has been equipped to make lots of really high quality scientific measurements. And so we got out there, and so this is a photograph of me standing in the hangar with the ER-2 behind it. And the other photograph is me there with a couple of my colleagues. That's Susan Solomon and Lamont Poole. Now, Lamont Poole went on to become a director of one of the branches at NASA Langley. Susan Solomon was for a long time a senior scientist at the NOAA Aeronomy Lab, and she's now a professor of climate change and climate policy at MIT. Susan was also awarded the Presidential Medal of Science a few years ago, and she also was part of the team. She was the chairperson of one of the working groups for the International Panel on Climate Change, and so she shared the Nobel Peace Prize in recognition of the work of IPCC, and went to Stockholm and received the prize. So we do work that's pretty cool and pretty important. I was at the Met Office at that time. The Met Office also had some pretty cool research aircraft. Not quite as beautiful as an ER-2, but this is a converted C-130 Hercules. It's one of the transport planes that are used by a lot of military people. And we were given one of these to play with, and so we took the nose off of this thing where there's usually a radar dome, and that radar dome is now sitting up above the aircraft, and we put this long striped nose boom that poked out of the front of the aircraft that allowed us to sample the air that wasn't being disturbed by the C-130, and that was the team of folks that I worked with down there. As part of that, I don't know if we were in the right place or the wrong place, but we had some expertise when the first Gulf War started, and we were asked to understand whether Saddam Hussein, who was then still in charge in Iraq, and he invaded Kuwait, and he was threatening that if the Allied forces, the Americans and the British come in to kick him out of Kuwait, that he would set fire to all the oil wells, and that there was some concern that that could be a major environmental disaster, that all that black smoke could rise up into the stratosphere, cover the earth in what's called a kind of nuclear winter type scenario. And so I was part of a task force that was asked to try and figure out whether that was a real possibility. And so we came up with some estimates, and we did a lot of studies, had to learn a lot of new things at that point, pretty much a scramble. And we gave some advice to our government, and there were some folks over in the US who were giving advice to the American government, and it was decided it wasn't a big risk that was going to happen. And then after the war, our bosses said, "That's great, we're now going to send you out on our aircraft to check your assumptions." So we get sent out to the Persian Gulf after the end of the war, and we were flying about chasing these smoke plumes and flying through these smoke plumes. And so this is a little video that we had some cameras mounted on the plane. And so this is an image from looking at the front of that aircraft with that big long striped boom as it was flying over the desert, and you can see some of the smoke there. And so I'll just play this little video. My wife tells me this is too long, so I'm going to jump it forward a little bit. So you see we're flying, we're banking over, and we're beginning to kind of get lined up on a smoke plume, and then we're going to straighten out, and you'll see, so that line at the angle, at that diagonal, that's the horizon. So we're actually banking along, but the camera looks like we're on the level all the time. We're going to see it straighten out. And then we're going to start to hit the side of a smoke plume. And what you're going to see is that as we hit the side of that smoke plume, we're going to straighten out, we're going to get in. So so it's now getting pretty dark. It's not too dark yet, but then as I'll move this forward a little bit, we go for it's getting a bit darker. So this is the middle of the day over the desert in Kuwait, and it's getting darker and darker and darker. And you see all these hoops that you saw on the stripe, they're all beginning to disappear because we can't see out the front of the aircraft. We literally can't see our noses in front of us. And it was right about this point I decided it was time to get a new job and to leave the Met Office. And so then, let me just move right to the very end. And so we were also even inside the aircraft, it would fill up with smoke and pollution. So we were actually all wearing gas masks. We were the only people, I think, out in the Persian Gulf during that war who were wearing gas masks. And this is a picture of it's probably not me, but one of my colleagues sitting up behind the pilots on the flight deck, and you see the technology he's got in his hand. That used to be pretty cool technology. That was the Cyan organizer from about 20 years ago. That used to be what was considered to be really state-of-the-art. And that was pretty important work. We were published in Nature, pretty significant journal. So after that, I then moved off to Germany, and I directed a small institute for stratospheric research, and we got working with the French, because the French have a lot of expertise in flying these large research balloons. So we were able to fly these balloons that would fly 30 kilometers up into the atmosphere. And we actually got work with some Russian scientists in the Russian Air Force. And this is a Geophysica. This is a Russian research aircraft. And so we had that instrumented up there. And so we had large teams. So Arena Arctica is a large hangar up in northern Sweden. And so we'd go up there and we'd be flying, we'd be doing investigations into the Arctic. After doing that for a few years, I was invited to become the director of the Atmospheric Chemistry Institute division at the National Center for Atmospheric Research in Boulder in Colorado. So I went there, and one of the experiments being involved in there, again you see, I'm kind of like a junkie for these fancy aircraft that can do all these cool measurements. And so one of the experiments we did was down over Mexico, where we were trying to understand all the pollution that's coming out of Mexico City, which is a mega city. So that's an image of the kind of inversion that's capping all this pollution inside the caldera, the basin that Mexico City sits in, and the mountain behind that is Popocatépetl. Try saying that 3 times fast. And it was really very, very polluted there. And the last image down there, that was a photograph from our hotel in Veracruz, 200 or 300 miles away from Mexico City, down on the coast. And we could only see these mountains at the very end of the day as the sun was setting, and it would set behind those mountains, and we'd just get a glimpse of those shadows. The rest of the time, we just saw this grey haze. And after doing that for a few years, I came down to Oak Ridge, and down here, Oak Ridge is the home of some of the most powerful supercomputers in the world. Titan is our latest version. But there's something wrong with that photograph. It should really be this photograph, because we don't do our scientific research by ourselves. We do it in teams. It's also pretty obvious. Not everybody in that photograph looks a lot like me. People are obviously coming from lots of different places around the world. Kate Evans there, she's one of the scientists. She's a mathematician, an atmospheric scientist. Daniela Toomey, she's doing a master's degree. She's from the Lebanon originally. She went to study hydrology at North Carolina. We hope she's going off to do a PhD soon, probably to Stanford. The guy behind her is Mo Ashfaq from Kashmir in Pakistan. He leads our regional modelling efforts in the group. The smiling guy behind me, that's Salil Mahajan. He's from India. He's one of the other climate modellers. The lady beside me, that's Marcia Brandstetter. She's a mathematician and hydrologist. And the guy who's shorter than me, he's standing closer so he looks taller, but he's actually shorter. That's Pat Worley, and he's a computer scientist, and he helps us understand how we run those models quickly. And so the point is, science is no longer an individual effort. Science is a real team effort. And when we do science, first of all, we get to do and tackle problems that are really worthwhile, problems that people really care about. We get to make some great friends that will be with us all of our lives from all over the world. We have great fun doing that. And we also get great resources to do that. We get these fancy aircraft to do that. Ian Anderson last week was talking about the most powerful neutron source in the world. We get to play with that here. And at Oak Ridge, we've also got the most, for the next 6 months at least, we've got the fastest supercomputer in the world. And even when we're not strictly the fastest, we're still one of the most capable supercomputers in the world because of the way we do that. And so it's a great future that you can have. You know, we are the true masters of the universe. We get to understand the universe, and sometimes you can get to change it a little bit. So that's why it's great to be a scientist. And I've been very grateful for the opportunities that I've had. Right, back to the lesson. So have we got most of the registrants out there? We've not got any people out there who are going to be left at the gate before we take off. Right, so thank you very much for being here today and taking the trouble on a Saturday morning and waking up from your sleep and all the other fun things you can do. My name is Danny McKenna. I'm a physicist, chemist and computational scientist at Oak Ridge National Laboratory. So today what I'd like to do is to tell you a little bit about how we model the climate system and how we try and understand climate, and also talk a little bit about what we mean by models. There's lots of types of models. Mostly what we do in these supercomputers is those are what we would call numerical models, but there's lots of other types of models. And it's just a little warm-up. I'd like to just show you this little video. Some of the folks who got here earlier have seen this already, but what's coming there? So this is just some tourists who've gone to look at the edge of a glacier that's flowing out over a fjord up in Alaska, and they're getting excited because it's beginning to calve a little bit, but they're going to get a surprise in a minute because it's going to be a little bit more significant than that. So they think this is pretty cool at this point, but any minute now. And see where this wall of ice just comes down. Right, so they're now thinking twice about whether they're in a good place at this point. what happens next. Right, that's one of the kind of physical processes that we have to think about in climate models. When we're dealing with some of these big beam experiments, what we're trying to do is to shrink down our uncertainties and look at one very narrow part of that. When we're understanding the climate system and trying to simulate the climate system, then we don't really have that luxury. We've got to really try and think about everything at the same time, but we do try and break it down into little parts and get models of the little parts, and then take all those individual models and try and group them all together. But there's lots of different types of models, and this is your first audience participation opportunity this morning, so I hope you're all awake. So what's going to happen to all that ice that plunged into the ocean? It's all going to bob about, and so the sea level has risen a little bit because the ice landed in there. But what's going to happen next? The ice is still there, it's still solid ice. It's now going to melt. What's that going to do to sea level? Josh?
Nothing. The ice is floating in the water.
Right, we're going to... Right, so...
When it melts, it will still have the same volume in the water.
That's you're quite right there, Josh. But so... but we're going to... Sometimes what we could do to test that sort of theory is we actually do a physical model of those things. That's what we're going to set up to do here. So... I need a couple of volunteers to help me with this. Josh, I think you need to be one of them, and I think the young lady beside you this time. There's going to be other opportunities, so don't worry. We're going to have another little safety briefing at this point. When I was early on in my career, I had a couple of incidents in laboratories that could have been really bad accidents. I could have perhaps in one instance lost my eyesight, in another instance lost the use of my hand. But because I was using good laboratory practice and I was using the right safety equipment, nothing bad happened to me. And so that's something that as you go forward as scientists, you've always got to bear in mind that you've got to think about safety, particularly when you're doing things in the lab. We deal with some pretty exciting stuff, but we always have to try and be safe. So today we're going to deal with something that's not particularly dangerous, but we're going to be dealing with some large blocks of ice. So the ice is cold, so there's a potential that we could allow the ice to slip out of our hands or numb our hands, and so we've got some safety equipment for you. I'm just going to try those on. Let's see, make sure those are open there. Yeah. There you go, Josh. You try those on. And here we have my passive cryogenic transport system. You might think it's a cool box.
Basically, I believe that it works because the heat cannot go through it very fast.
That's right. So, Josh, why don't you pick up this block at this point? Oh, actually, let's go for the other one first. Why don't you put that down? Pick up that guy there. Right, so we're going to simulate an iceberg at this point, so I'd like you to be careful. We don't want that big wave, Josh, do we?
Right.
No, so you want to carefully place that in there. Don't just drop it, but carefully lower it down.
However, I can't lower it very far.
Right. Well done. Right, now, so Hannah, why don't you pick up this other piece and see if you can carefully lower it on top of that.
It's got a handle on it, so it should be easier.
Right, just let go. Right, so there we have our model of an iceberg. Just let the other people see it as well. Now, this is not working very well. I thought you could maybe see this on projection.
Idea. Maybe we can add a few more ice cubes so it is just exactly filled to the rim. Then, if this water level rises, we won't see because it overflows.
Yes, and it will ruin all of that paper. That's a good idea. I thought about that beforehand, but decided not to bother. But there's another way we can maybe track what's going on in here. If you would like to trace the outline of the shadow cast by the ice cubes. Can you see that? Can you see the shadow there? Can we dim the lights a little bit at the point? Could somebody help us with dimming the lights? There we go.
Like that?
Right, so that's good. So we'll just see how that goes over the course of the day. I remember, so please give me back your safety equipment. Thank you very much. You both did a marvellous job, and you can now safely go back to your seats. So when I was a young boy, I had a book called Tell Me Why, and it used to say, this is not really to do with our lecture, but always one of the things that struck me, it was Tell Me Why, and it would say, isn't it amazing about an iceberg? It would say something like 9/10 of the iceberg are below the surface of the water. And I thought, well, that's, when I began to understand more about science, that's not really the amazing thing about an iceberg. The amazing thing about an iceberg is that kind of 1/10 floats up above the water. Because ice is the only, frozen water is the only substance that you'll really come across in everyday life that will float in a molten solution of its own substance. Nothing else really does that. Anything else, you take a solid part of itself and drop it into a molten tank of itself, it will sink. And that's one of the very peculiar and interesting and important properties of ice. Not really got much to do with what we're talking today, but it's an interesting part about ice. So that's a physical model. If we didn't have Joss here, that would be one of the ways we would answer the question as to whether we can, whether the ice will rise or fall or so on. But we've also got different types of models. We've got that physical model for how the water level rises. We've got mental models. So now I need another volunteer. This young lady in the front in the black shirt. Are you good at, do you enjoy playing baseball?
I suppose.
You suppose. Well, perhaps you could put on this. So, let's see if I can still do that. Yes, I can still be managing. Now, if you'd like to stand over here.
I'm not left-handed.
There's a left-handed glove. Right. And if you stand over there and just be ready, I'm just going to throw you one or two simple balls, right? We're going to illustrate something. So, are you ready to catch this? Right, well done. Now, what we did there was that Victoria really had a mental model of what a ball does when it flies through the air. And she was watching what I did, and she was able to match that model to the behaviour of the ball and catch the ball. She was doing, in the background in her brain, she was doing millions of calculations to make that happening. Are you feeling okay? You're not too exhausted with that? No. So now we're going to do something a little bit more difficult. So I'm going to not just throw it simply to you, I'm going to make you do a little bit more work. But I still want you to try and catch it. You maybe want to take that ball out of there. We just drop that one to the side just now. Now, be ready to catch this. It's going to maybe fall a little bit short. Right, so she still caught it, even though the model changed. Yes, give her a round of applause. Even though it wasn't exactly the same trajectory, I changed the way the trajectory was, but Victoria was able to observe what I did, process that information, update her model, and actually still put her hand in the place where that ball would be. So lots and lots of calculations in the brain. So if you're ever actually doing baseball and you want to go back into your math class and maybe your teacher's giving you a hard time because you may be not paying enough attention, you could just explain to us as well, you know, Miss so-and-so or Sir, you know, that really, I've been doing lots of calculations on the sports field already today, and I'm just exhausted with that. I've done all the math that I can really do today. So thank you very much, Victoria. And so that's an example of a mental model. We've got these models in our brain that change things. We also have simplified models. Now, Joss, last week Ian showed us a sieve, and he said it was two-dimensional. Do you remember what you said to him at that point?
It's a lot thicker than two-dimensional.
It's a lot thicker. It's a three-dimensional object, and you're absolutely correct. But Ian wasn't incorrect either, because what Ian was doing was saying that for all practical purposes, we can simplify the model that we have for the sieve, and that we're going to get that grid, and it's really the property, the two-dimensionality, the approximate two-dimensionality of the grid, which is what gives us the diffraction pattern that we see. And so you were correct, but Ian was correct as well. It's because what we were doing is we're choosing what are the most important aspects of our model to get the effects we need. And we do that often when we're dealing with these sort of situations in other types of models. We have to choose to simplify the models, and part of the skill in being a modeler is choosing which are the things to simplify and which are the things that we really need to pay attention to. Right, now, there's other types of models we've got. Now, this is another audience participation opportunity. I'd like everybody who thinks it's going to be warmer than it is today tomorrow to stand up. Okay, thank you. So now I'd like everybody who thinks, one of the volunteers at the back was mentioning to me that there might be an exercise a couple of weeks from now that'll be outside, and she was being worried about, I think it was Julia, she was worried, or Julie, about whether, hi Julie, about whether we could go outside to do one of the exercises in a couple of weeks. So how many people think it's going to be warmer 2 weeks from now on Saturday? How many people know it's going to be warmer or colder? Now, that's it. So you guys all know it's going to be warmer 2 weeks from now? Really? Okay, thank you. Now, you guys are pretty confident, and I'm not sure you should be sure about that it's going to definitely be warmer. About 4 months from now, we're so in February just now, what month are we going to be in 4 months from now? I can't hear you. June? So June. So I'd like everybody to stand up who thinks it's going to be warmer in the first Saturday in June than it is today. Now, is there anyone sitting down? Ah, come on, do so. Right, so pretty much everybody thinks it's going to be warmer then. So what that really tells you, there's two things. So thanks very much. You can sit down now. So that tells you two things. First of all, you've got a statistical model for the temperature here in Knoxville. You've got an idea about when it's going to be warm and when it's going to be cold. Some of you thought it was going to be warmer in 2 weeks. I'd like to take a bet on that one. I think I could win some money on that.
You have the computer though.
That's right. But you're all pretty sure that it was going to be warmer 6 months from now or 4 months from now, even without a computer. You're pretty confident, and that's because you've got a mental model. You know that essentially it's colder in the winter and it's warmer in the summer. So that's what we would call a statistical model. It also tells us you know something about the climate system. You know something about the difference between climate and weather. So weather is what tells us whether it's going to be warm or cold tomorrow, and it's climate that's really telling us about whether it's going to be warmer or colder about 6 months from now. And so we think about weather being something that changes over time in the atmosphere. Weather happens every day, we get different weather. Whereas climate is really about what happens in that long-term average. It's what happens over time. And so the climate of a system may be quite different from the particular weather you would get in any individual day. I can't remember what sort of model this is next. Right, so what would happen if the climate changes? There's a number of things you can do. So what this graph shows is we've got on the axis, we've got a scale that's going from cold to hot. I'm going to see if I can probably use this guy, can't I? We've got a scale that goes from cold to hot, and at the present time we have what's called a probability distribution function. So it tells us that it's likely to, the temperature just now is likely to fall around about in that day, and we can expect that there's a certain number of days in the year where the temperature will fall about this kind of mean temperature, and then some days are going to be colder and some days are going to be warmer. Now, if climate changes, one of the ways it could change is that this whole distribution just shifts up. So the likelihood of cold and warm days, relatively cold and relatively warm days, could stay the same, but the mean just shifts up. But what we would say, the variability of the weather doesn't change very much, or the climate. Or you could get a situation where it moves up and also becomes less variable, that you're in a situation where it's more likely to fall around this new mean temperature. Now, I have to be sure I don't point the laser pointer at people. But that we could have a more narrow distribution. So that's a possibility of the way climate would change. Or we could actually be in a situation where it becomes even much more variable, that we've got the chance of big extremes, both extremes to be very hot weather, so droughts and hot weather events, and also very cold weather events. That's another possibility. The mean still shifts up, so the mean average climate state getting warmer is still becoming warmer than it was before. But there's still the possibility that you could get cold days, and the possibility you could get very hot days. And so that's one of the kind of confounding factors when you're trying to deal with climate, is that just because you maybe get some days that are cold, that doesn't disprove that climate has changed. It's a possibility that that's the way the climate system would behave. Now, we try and understand the way climate works in a number of different ways. We try and use historical data whenever we can get it. Have people heard about tree rings? Do people know about tree rings? So a lot of you know about tree rings, and so people count tree rings and they look at the thickness of the tree rings, and because a tree every year adds on another layer, then we can look at how climate and weather has changed over time. We can do something similar to that if we go to the polar ice caps down in the South Pole, and actually up on the Greenland ice cap as well. We have, every year, there's an extra accumulation of snow as the snow falls on the landmass. And so each year brings another layer of snow, and that accumulation of snow can trap air in tiny bubbles, and we can go back and we can measure the properties of that air with some very sophisticated equipment. And we can count layers in the ice, and so just like with tree rings, we can count back in time and we can place particular bubbles at a particular time in the past, and we can get some information about the atmosphere that way. One of the things we can do with that is we can get the amount of carbon dioxide that's been in the atmosphere, and this is what this shows here. This is 400,000 years, so this is almost what you would call deep time. So we've gone back, and people, I'm not sure I would like to do this sort of research, but some people really love to go back and count each one of those individual rings and to measure the carbon dioxide concentration in it. And you see the carbon dioxide concentration has varied up and down, and it's varied from about 200 or just under 200 up to just below 300 for the last 400,000 years. Now, in the last few years, we've been doing something pretty funky to the atmosphere. We've been burning lots of fossil fuels. And because of that, that's adding extra carbon dioxide into the atmosphere. And so in around about 2005, we'd gone up to about just over 350,000 parts per million. So 350 parts per million, that's still not a lot. That's less than 1 part in 1,000. So for every 1,000 molecules of air, there's still less than 1 CO2 molecule. So it's not a lot of carbon dioxide, but it can still have a big effect because of its effect on radiation. And if we continue to burn fossil fuels, then we project that the amount of carbon dioxide in the atmosphere is going to continue to go up. And that's one of the bases of why people get pretty excited and interested in climate. And if that sort of thing is going on, then we expect to see certain evidence of that in some of the other records. And so if we look at the record of global temperature from about the 1980s, around about 2000, we see there's been a fairly steady increase. It varies about, just in the same way weather can vary. You've got a question, yes?
But isn't in the, on the temperature chart, like that, those temperatures, back then, they didn't have the computer to make a model of the whole Earth. And back in the 1880s, that was mostly temperatures from the land. So
this is
looking at the whole data from the 1880s.
Well, there weren't as many observations, that's correct, but there were observations from the land and the sea. There was sailing ships going about, and you're right, they didn't have many computers and so on. But there have been people who have been, I'm not an expert in that area, but there are people who very carefully analyse those observations and the observations we have today, and they make an evaluation. There was quite a big controversy a few years ago about this, with people disputing as to whether that was the correct thing to do, but some new independent groups have come in who, if you like, haven't been part of that kind of tradition, and they've come in and they've looked at the techniques and the approaches to that, and they've kind of found that you still tend to get these sort of effects coming out. And so we believe this is pretty confident. And so what we're doing is this, we're looking at this relative to a time early in the last century. And you see that before that it was a bit cooler back in the 1880s. And that more recently temperature has begun to increase, and we're getting increases of about just over ½ degree centigrade. Does anyone know what that's in Fahrenheit? Josh, know what that's in Fahrenheit? What ½ degree centigrade is? What's that in Fahrenheit?
I'm not good at components like that.
Neither am I can't do that in my head either. But so we do have evidence from that and from other things that temperature seems to be rising. We also can look at glaciers. We saw that glacier calving off. Well, that's a process that's going on all the time. And if everything is equal, then glaciers are receiving new snow and ice at a constant rate, and so they're always calving off, but they're always being replenished from further back. And so over a long time period we expect a glacier, once it's been set up, to be fairly stable. But if things change, lots of things can change. The temperatures change, and so it melts faster. Weather patterns can change, and so the amount of accumulation of snow that's falling in the glacier can change. And over a period from, I think that's about 1989 through to just about 2008, we see that this is one particular glacier is retreating, and it's retreated quite substantially. If you do that globally and look at all of the glaciers, you'll find that there's maybe 2 or 3% of the glaciers are actually growing. They're still growing because the particular combination of extra precipitation and temperatures has actually added more mass to it, but that's only about 2 or 3%. The vast majority of all the glaciers around the world are actually melting and retreating and going back. A lot of the glaciers in the Himalayas are doing that. Mount Kilimanjaro used to have glaciers, and they're just about gone. Glacier National Park, by about 2100 there'll be no glaciers left in Glacier National Park, and isn't that Montana's Glacier Park? I think it is. So there's lots of reasons why the world is changing. And so what we do is we then start to devise theoretical models to try and understand the Earth. And so before we talked about the statistical model of knowing that it's warmer in the summer and it's cold in the winter. But at that point we didn't talk about, well, why is it warmer in the summer and why is it cold in the winter? Josh, do you know why it's cold in the winter and warm in the summer?
Because the Earth tilts. When it's tilted this way, And when our side is tilted toward the sun, then we're getting head-on radiation, giving us more heat. However, when we're tilted away, the same radiation is spread out more.
That's right. So basically, if you imagine this is the Earth and these are lines of latitude, then the Earth tilts at an axis as it spins round like this. And sometimes as it spins round, the northern hemisphere is pointing a little bit more closely to the sun. We're going to simulate this lamp as the sun. And so the northern hemisphere, and that's the summer in the northern hemisphere, and so we get extra sunlight during that period. And then during the winter, we're actually tilted away from it because we've moved round and we're in a different position. And it's the sun, and it's then the southern hemisphere that gets the extra sun. And that's why the sun is why the summer is warmer than the winter. And what we've done there is we've developed a theory. That's a theory for why it's warmer in the summer and closer. So that's a theoretical model. And so we can explain some things, but that really doesn't, that model by itself doesn't tell us too much in detail about how warm it's going to be in the summer and how cold it's going to be in the winter. And so we need to then go to more detailed, sophisticated models, and that's when we start to really build on these numerical models that I spend a lot of my time sort of running, and lots of my colleagues spend time building and running and simulating. And you know, the Earth system is really, really complex. In the kind of last couple of centuries, and since science really took off, there's really been a philosophy of what you call reductionism. So you take things that are really, really complex and you break it down into a lot of pieces, small pieces that you can individually understand, and you can get a lot of understanding from that. And that's been one of the great successes of the kind of scientific approach over the last couple of hundred years. But what we're beginning to find in a number of areas, and climate science is one of those areas, is that when we do those things, we still don't fully understand the system. There are things, what we call emergent properties, that you can look at all the individual components and it'd be very hard to predict what those are. So, for instance, if you understand water vapor and water and condensation, and you understand that when water condenses, it gives up energy, it gives up latent heat, and when it evaporates, it cools down and takes up that latent heat. You can understand all about that. You can understand all about the thermodynamics of air parcels moving, but it'd be very difficult from just thinking about those simple systems to predict the existence of hurricanes. But that's all that hurricanes are really all about. Hurricanes are really these engines that do this thermodynamic processing that's going on. And so in climate models, or what we now usually tend to call them as Earth system models, because the climate is a very important part of the Earth system, but in order to really understand climate of the atmosphere, we have to understand many, many more components. We have to almost understand the entire Earth system. We have to understand about the oceans. We have to understand about the land and about the take-up of carbon dioxide by plants, and about the changes in albedo. I might lose that. I forget who I was if I lost that. We have changes in how much the land reflects energy back to the sun because of changes in the vegetation. Changes in the amount of rain that falls on the land can change the vegetation. And so there are many, many components that we have to understand in order to understand the climate system, and even in the Earth system. Now we do that by, a lot of what we do that is that we have these incredibly complex mathematical equations, and we have to describe them from the entire Earth. And we do these, and so this is what some of these equations look like. Now, some of them are telling us pretty simple things. So this one down here, this equation, that's really telling us about the thermal energy in the atmosphere. It may not look like it to you, but that's an equation that tells us how air expands and contracts and how things are buoyant and so on. Up here, that equation, that's just telling us is that we we can't compress the atmosphere too much, that we've got a gas and it's going to stay in a particular state. In this equation here, have people learned about the equations of motion, Newton's equations of motion in school? So you've got various laws, and so you understand about the velocity of a cart moving about. Well done, not many people seem to have learned that. You should have been paying attention, those things are important. Well, this equation is the way we represent the equations of motion in the atmosphere. So we'll get G here, that's acceleration due to gravity. We've got velocities here from how air rises up or sinks down, and then how the velocity of air or wind as it moves about. And so we can describe the atmosphere with these sort of equations. But it becomes almost impossible for us to solve those equations with a pen and a piece of paper, or a pencil and a piece of paper. It's going to take us forever to do that, and we're not very confident that we can do that. There are prizes offered to mathematicians just to prove some simple property of these equations, and so we can't wait for solutions like that to come along. So we've got to use different strategies, and one of the strategies we use is we break this entire complex system up into lots and lots of little small components. We say we put a grid, we discretize the model, and so we then have lots of little boxes, and what we're going to then do is we're going to look at each individual box and try and understand what happens there, how energy moves about and how moisture moves about in these individual boxes. And when we started off, we would use grids that looked like latitudes and longitudes. And so if you imagine this as a model of the Earth, then these lines down here are lines of longitude. They tell us how far east or how far west we go. And there'll be also parallel lines that would tell us about which latitude we are. And so if we're at high latitude, then it's typically colder, and if we go down to low latitude, we'll get to the equator, and it's usually warmer there. And that's the way we would normally think of the coordinates for the way we'd understand a model of the Earth. Now, one of the problems that we have with that is that as we get towards the North Pole and the South Pole, all these lines of longitude bunch together. And so we would like our little boxes to each represent the same amount of the atmosphere, but we have a problem because as they get closer to there, they represent smaller and smaller boxes. We say the resolution is changing near the pole. And so we then start to come up with these funky grids to try and take account of that. And so this is one example of this, what we call a cubed sphere, where we take a sphere and we take basically 6 squares and we drop it over that cube and we kind of stretch them. Imagine they're like elasticated membranes, and we stretch them over there, and so we get these distorted grid, but it almost looks like a cube, and so we can do lots of sums with that. We can also do other things. We can have these hexagonal grids, which are based on an icosahedron, and so there's some similarity between those grids. And if you remember last week when you were dealing with the buckyballs, and you make up a buckyball and it's made up of lots of little hexagons and pentagons, and so that's kind of what's going on in here. We've got mostly hexagons in here, and if you look very closely, you would probably find 1 or 2 pentagons. And again, that allows us to adapt our grid to really complex shapes. So these are often very useful if we're trying to understand the ocean, where we get really complex coastlines, and so we can use these complex grids, and then we can simulate all these really elaborate features that are going on in the ocean. Like this is the Gulf Stream, which you see it meanders back and forward. It's very complex, and so you need very fine grids there. So there's another type of grid, we call this an icosahedral grid, where we take an icosahedron and we drop it on to the Earth. And then an icosahedron, each of the faces of an icosahedron are basically an equilateral triangle. And so for any equilateral triangle, you can fill an equilateral triangle with 9 equilateral triangles that are smaller than that, or 6. It's 6, isn't it? Josh, isn't it 6? 6 equilateral triangles in a... You can fit 6 smaller equilateral triangles into... Or is it 4? It's 4. It's only 4. That just goes to show you something about some people in the world. There are only 3 types of people. There are people who are good at mathematics, and people who are not good at mathematics. The people who laughed got that one. I'm obviously in that second group. I'm in the group, the people who are not good at mathematics, because I can't count how many groups there are, you see. Right, so I'd like to introduce Jennifer, our master teacher. Give Jennifer a round of applause. Jennifer's been working very hard behind the scenes preparing a lot of these exercises, so now we're going to give you a chance to do some stuff, and so I'm going to let Jennifer take over from here for a minute.
All right. Am I on? I can just yell. Okay. You are going to be building one of these, a model of the Earth, to show you how we can take this triangular grid and actually use it to model something that is spherical. And you're going to see how close to a sphere you can end up being. So you're going to start with something that looks like this, where you're going to see all the little triangles, and the triangles are going to be connected by these little tabs. So step one, whenever you get to where you're going, is going to be to cut this out. So make sure that you cut only around the edges of your diagram and leave the little tabs in place. Can you see those white tabs? Those are really important. Without the white tabs, you're not going to be able to turn it into an Earth. So once you have it cut out like that, you'll take glue and put glue on each little tab and glue the tabs to the underside of the triangle that they're next to. Do one whole hemisphere first. Do the northern hemisphere first, and then you can do the bottom hemisphere. It'll work a little bit easier for you. So that when you finish, you'll have an Earth, and you can see the grid that's on the Earth and compare it to what we're talking about with modeling. Sound like something you can do? Yeah? We have 2 rooms set up for you. So when you come out the door into the lobby, you're going to go to the left down the hallway, and you're going to see people directing you. So make sure you pay attention. So some of you are going to go in one room and some of you into another. So let's go out that back door and head to your left.
Can we drop the lights down a little bit here? I think some of these will show up better with slightly darker. And so this is what you call a high resolution simulation of the cloud and precipitation. And so you can really begin to get a sense of the way weather patterns work, and you get these crashing flows of air. We're really running out of time. I just enjoy talking so much that I'm way behind in terms of what I should be doing. My time management is terrible, so I apologize. So we're going to be going through this little bit, this part a little bit quicker than usual. So we can also use the models to tell us about whether what we understand about the impact of CO2 might be right or wrong. And what we're showing here in this plot, if I can find my laser pointer that I put down someplace. That's another of my characteristics. Oh, there it is, yes, thank you. One of my characteristics is losing pieces of equipment. And so what it here is we've tried to simulate the observed temperature trace. And this is for a model where we don't actually put in any CO2 increase into the model. Whereas if we put a CO2 increase into the model and we take some other kind of appropriate steps, then we see we begin to simulate something that looks like it's showing the sort of trends in temperatures that we observe. It's not exact. Not all models are wrong. That model is clearly wrong. This model is still wrong, but perhaps this model is more useful in terms of describing what's going on in the atmosphere. And then we can actually begin to ask, well, what's going to happen next? So this is I'm just going to advance through this because I'll talk through it, some of it as we go along. So what we're seeing up here is a model of the kind of surface temperature starting about 1970. Each one of those, you see these years are clicking by, and we're about 0.4 degrees C below the average, and it's jumping about, and we're seeing this trace here of the temperature. And as we get these volcanoes, you see when a volcano erupts, we get this cooling happening. You see how it gets cool up here, the temperature then recovers back up. And so each of these volcanoes, and these are really good tests for us so that we can put in the effects of the volcano into the model. And it's like taking the atmosphere and hammering, hitting it with a hammer and watching it ring, so we get these transient effects. And so that tests our model and our understanding of the physics in a slightly different way. And as we're going along, we see that it's simulating the change, and we're getting these little dips, but the temperature is rising up a little bit, so we're not seeing quite as much blue. El Chichon, that probably happened in my lifetime. Pinatubo, were you alive when Pinatubo happened? People heard of Pinatubo? Maybe not. And then we can go on to the future. What happens next? What's going to happen in the future? Well, if we do nothing and we stop all CO2 emissions, we're committed to a certain amount of CO2, which is what this trace would be here, and so that's telling us the temperature is still going to rise. If we take the scenario B1, and these are scenarios that scientists have decided as a reasonable estimate of what might happen if CO2 stabilized at 550 parts per million, then we would follow this trace here. Or if it stabilizes at 720, which is what this graphic is showing us, we would follow that trace there. And you see that by 2001, it's not, we've talked about half a degree of change that we've already observed since about the 1880s, but we might be expecting more like 2 or 3 degrees of climate change as we go to the end of the next century. Now, what we do is we use very powerful supercomputers to simulate the climate. But the interesting thing about a supercomputer is it contains processors that are not that different from the processors you might find in the smartphone that you might have in your pocket, or in the laptop that you might use for your homework. And so it's kind of unusual. Why is it a supercomputer when all you've got are the same sort of processors that you've got in your cell phone? Well, first of all, there's a lot of them. We have a very, very large number of processors, and depending on how many processors we've got, we ask these processors to do different amounts of work. So in a low resolution model, we might spread the process around different tasks. Some models are doing the ocean data. It takes a long time to do ocean calculations. Some are calculating things for the atmosphere, some about the land surfaces, some about the sea, and some about are coupling all these different things together. Now, if we then change the resolution so we go to a much finer grid that we've got, then suddenly the way we have to spread those processes out changes. So that becomes part of the skill of doing supercomputers, is to decide how we leave those processors. Now, I'm guessing one or two of you have watched The Hobbit, and the question is, would you rather, if you're going to race someone, would you rather be riding a warg, or would you rather be riding Radagast raising Rossignol rabbits? Try saying that quickly. And basically, Radagast has got a technology that allows him to harness all those rabbits together. So he's got a sled with all of these rabbits tied together, and so these rabbits can actually outrun a warg. A warg is a much bigger, more powerful animal, but putting them together and harnessing them and organising them, they can actually go in the right direction and can actually outrun a warg. Well, that's kind of what it's like when we do supercomputer simulations. We've got, some people say, ask, would you rather have a cart that's pulled by 1 horse or by 1,024 chickens? Well, actually 1,024 chickens, if you could make them all go in the same direction, that would be a pretty powerful cart. So now we're going to try and ask you as an exercise when you go home, because we've run out of time. I'm sorry about that. I've enjoyed myself. Have you enjoyed yourself? Excellent, thanks very much, that's good. We're going to give you an exercise to take home, and you're going to be simulating individual Roscoe rabbits. And so we're going to give you an exercise to take away. One of the things we do in the models is we simulate sea ice. And so Jennifer is now going to tell you a little bit what this exercise we're going to do. And we're going to give you an opportunity. There's going to be a website with a spreadsheet where you're each going to be able to put in your numbers, and we're going to construct together a simulation of how sea ice is changing in the Arctic over the last 25 years or so. And what you'll see from that is that you're behaving like individual processors in a supercomputer. You can each go away and you can do those calculations and do that exercise in parallel. And that happens much faster than one person doing 35 calculations. Then you get 35 people that can do that much faster. And that's the way basically a supercomputer works for problems where you can break it down and all the processors are doing roughly the same sort of job. Then we can do things that are much faster than they would be otherwise. Do you want to use this guy?
We could probably use that. We'll make it work.
When you leave the auditorium here in a little while, you're going to go out to a table and pick up some materials to take home with you. So we want you to grab a grid like this printed on transparency. This is your plonker. And you're also going to grab a picture that shows, looking down at the North Pole, you can see the white part is the sea ice that is present during the year that's printed on your picture. So you can see whenever you get your picture, you've got the white part that's sea ice and the years, really important. Each one of you is going to get a different year because we need you to work together. Each one of you is an individual rabbit, and we're going to use all of your data to make sure that we can get the answer to our question. You're also going to pick up a dry erase marker and a piece of paper that has the URL where you're going to use this information. So what we want you to do is take your image of sea ice and lay your plonker down on top of it. And
plonk it on top.
Plonk it on top. Plonk it because it's a plonker. On top of your picture of the sea ice, and use your marker to trace around the outside of the ice. Don't worry about this pink line, so trace around the outside of the white. Once you've traced it onto your grid, we want you to count the number of little tiny boxes you have that are covered in sea ice. The boxes are really small. So inside of this one larger box, you have 100 smaller boxes. So we want you to count how many there are. Now, you don't have to sit there and count every single box, right? If the white part fills up this entire big box, you know that that's 100. Just write it down and go, right? So after you've counted how many little tiny blocks per larger block you have that are filled with sea ice, you can add them all up and come up with a number. This is the number of blocks that are covered by sea ice in 1979. And what we want you to do is go to the website on the piece of paper that we're going to give you, and you're going to see a table. On the table, put in the year that you have, 1979, the number of blocks that are covered by ice. I don't know, it'll be something around 2,000, somewhere around there, you know, give or take. You have to count exactly right. And then you'll put your initials in the block next to it. So now you've given us your individual data as a rabbit. Now if you come back in about a week to that website, you can click the tabs along the bottom and you'll be able to see the graph of everybody's data, and you'll be able to see what all the rabbits working together were able to do. And you should be able to see the change in sea ice over time. If you come back next Saturday, we offer this 2 Saturdays from now, then we're going to show you that data up on the screen. But you can also check it out from home by clicking on the links at the bottom. Sound good? All right, turn you back over.
Right, and
you don't need that.
Well, yeah, that's right. So I'd just like to also just remind you that I mentioned earlier when I was talking that science is a team game, and today's been no different from any other day. There's been a team of volunteers and helpers who've been making all this happen. Jennifer has been doing a lot of work to prepare for this. Marie has been doing a lot of work, and there are helpers all there as well. So I'd like you to join me and give them all a round of applause. And thanks very much for coming and showing some interest in this, and we really appreciate you doing this. Yes, we've got
I had one question. Do we need to do all of there's some white that's away from the main body? Should we do all of those too?
If you want to do the best job on this, we're just going to count the white that is connected to itself. So for the sake of...
Oh, sorry, I need to take that off because... sorry.
To make sure that we're all doing the same thing, we won't count any white that's not connected. So let's not worry about these little teeny tiny pieces out here. We'll just count the white that's all connected to itself. That's a wonderful question. I'm glad you asked that. Do you have another question?
Yeah, what if it covers like half of the box?
Oh, great question. If it covers half of the box, then you should look and see if you have another half of the box that's also covered and count it as one. We don't want to have fractions. The boxes are so tiny. Whenever you see it, you're gonna think, oh my goodness, there's no way I could even get a half of something to fit in this box. So if you have two halves, count it as a whole. But don't worry about having a half left over. Don't tell me 2,194.5. That's a great question. Does anyone else have any more questions? I'm glad you're so excited about doing this. You're going to be good rabbits.
Yes, and you get a piece of lettuce or some carrot afterwards.
Okay.
Thanks very much.